All right, so 8, 123. If the core electrons are 100% effective at shielding the valence electrons, so that means they're going to take up, each electron is going to take up 1 proton, right, from the nuclear charge, and the valence electrons provide no shielding for each other. What would be the effective nuclear charge felt by sodium? So if we looked at sodium, we see that sodium has 1 extra it has 11 protons and 10 core electrons. So 11 protons, 10 core electrons. So there's a +1 charge that the valence electron is going to feel. All right. So for the other, what's the other one here? For sulfur, sulfur has 16 protons. 16 protons. We'll draw a picture of this one for you. 16 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. 16 protons in there, right? 16 plus charges. And it has core electrons are 10 going to neon, right? So the core has 10 electrons in it. Now the valence electrons, there's 6 valence electrons, and the question is, what do those 6 valence electrons feel? Well, they feel the difference here, which is a +6. All right, and then the last one is chlorine. Chlorine has 17 electrons, 10 valence electrons, so it's going to feel a +7. 17 protons, 10 valence electrons, so it's going to feel a +7. All right, 8, 125. Choose the larger atom in each pair. Okay? Larger atom in each pair. Choose the larger atom in the pair, magnesium or sulfur. So going from left to right on the periodic table, our larger atoms will be the ones on the left. Magnesium, so magnesium will be smaller or larger than sulfur. All the extra electrons that are being added in to the atom from going from magnesium to sulfur are in the same shell. All right, so looking at acetane or bismuth. Acetane or bismuth. Bismuth will be larger because we have electrons in the a much higher shell. All right. 127. Choose the larger atom, germanium, from among the following: germanium, acetane, tin, or antimony. Germanium, acetane, tin, or antimony. Okay, so based on this, I would choose tin, but I think, let's take a look here. If we look between tin and antimony, antimony is actually a little bit larger than tin. But there's no trends that are discussed in there. You see that as we look on the periodic table on page 342, I'm looking on page 342, you can look at the trends here, and you see as we move from left to right, these gray circles, the sizes get smaller as the electrons fill in. But here, tin and acetane, tin and antimony, they're almost identical, with antimony being slightly larger, but the trend continues with beryllium, iodine, and xenon. Okay, and 1, 2, 3. 1, 2, 3. Yeah, there's no real good explanation for why antimony is smaller. Or there's probably a good one, but it's outside the scope of this class, and I'm not aware of it. So that's kind of a bad question, because the trends that they do identify to us are simply left to right and effective nuclear charge, and as we fill the electrons. So it should be, well, I mean, you would predict to be 10, but we see here that it's antimony. So that's not really a good question. You wouldn't be able to answer that without that table there. All right, what's the next question? 129. Choose the larger particles in each pair, sodium or the sodium atom. Well, sodium metal is going to be larger than the ion because the ion removes an electron. Cobalt 3 or cobalt 2? Cobalt 2 is going to be, wait, we're looking at the larger particle. Cobalt 2 is going to be larger because cobalt 3 has one less electron. Chlorine atoms are going to be larger than chlorine ions. So that's 8 to 129. Okay, now we're on to 8 to 131. Choose the atom with the larger ionization energy in each pair. The larger ionization energy. Well, ionization energy trends, you can look at, remind yourself of those on page 346, but generally it's left to right and bottom to top, increasing ionization energy. So if we look at boron or nitrogen, the ionization energy increases going from left to right. So nitrogen would be higher. Selenium or sulfur. Sulfur is going bottom to top, so sulfur would be higher. Chlorine to germanium. Chlorine is higher and to the right than germanium, so chlorine would be higher. Choose the atom with the larger ionization energy. So we chose nitrogen, sulfur, and chlorine. Let's double check those for 131. Nitrogen, sulfur, and chlorine. Nitrogen, sulfur, and chlorine. All right, 8 to 133. Choose the atom with the more exothermic electron affinity in each pair. Iodine or bromine, gallium or arsenic. So what we're looking for here is we're trying to find out that when exothermic electron affinity, so when it gains an electron, which one will release more energy? Again, if it is going to be gaining an electron, which one will be more exothermic? All right. So we look at page 133, and electron affinity energies increase from the going to the right of the periodic table and up, right? So we would expect the one to be more exothermic in gaining an electron affinity to be bromine for number 133, and we would expect in the other pair, what's the other pair? Gallium or arsenic. Arsenic we would expect because it's further to the right. Okay? And the way you can kind of think of that is if bromine gains an electron, it's like adding one more to the 35 that it already has. And so it influences the energetics around that atom more than, let's say, iodine receiving an electron. Because when iodine received an electron, it's just one more to 53. So it's less of a fraction, smaller percentage of electron added, right? So 1/53rd of all the electrons, and that's how much energy is going to be gained, or 1/35th relative to bromine, right? And the same with gallium and arsenic. Okay? 135. Use the periodic table to select the element in the following list which there is the largest difference between the second and third ionization energy. All right? So to determine the second and the third ionization energy, largest between the second and the third ionization energy. So what we need to do is we need to use our periodic table here and look at the elements. Now, there's that table on page, let me put this in here real quick. table on page 347 that shows that as we, it's figure 832, and it's showing the different energies, the different ionization energies associated with the different elements. Not all of them, but some of them, right? We have fluorine, oxygen, nitrogen, carbon, bromine, beryllium, and lithium, right? Again, this is page 347, this one here, this figure here, right? And we see this bar here represents how much energy it requires for fluorine to give up 1 electron. This is how much energy it requires for it to give up its second electron. It is 3rd, 4th, 5th, 6th, and 7th. And you see that there's a gradual increase. But from the 7th to go to the 8th, there's a huge increase because the 8th electron of fluorine is part of its noble gas core, right? So when we're looking to answer this question, what we're wondering is, it says which one is going to have the largest difference between the 2nd and 3rd. Or in other words, when the 3rd electron being removed goes into its noble gas core, all right? So if we look at the first one, sodium. Sodium, you remove 1 electron, and that's a valence electron, and now you're at the noble gas core of neon. So if you remove your 2nd electron, that one will be very hard relative to the first one for sodium. So the largest difference will be between the 1st and the 2nd, right? But that's not what we're looking for. We're using the periodic table to determine the largest difference between the 2nd and the 3rd, okay? Magnesium. Magnesium, you lose 1 and you become sodium. That's the valence electron, so that's not, it requires energy, but not much. You lose a 2nd, then it becomes neon, and that requires energy, but not as much. But then if you're going to remove a 3rd, you're going to go into the neon noble gas core, and so that's going to require the largest amount of energy, the largest difference in energy between the 2nd and the 3rd. And that's what we're looking for, so magnesium is going to be the answer. We can do aluminum while we're here, but it's going to be the largest difference for aluminum is going to be between the, not the 1st, not the 2nd, not the 3rd, but between the 3rd and the 4th. And silicon is the 4th and the 5th, and nitrogen is the, not the 1st, not the 2nd, not the 3rd, not the 4th, but, and not the 5th, but the 5th to the 6th. If you remove the 6th and try to pull 1 out of the helium noble gas core. Okay? So the answer there is going to be, what do we say, magnesium. All right, there we go, 135, that's the last one.